Hey, welcome back to Computer Science Theory. This is COMS W3261, offered Summer B 2021 at Columbia University. And this is Lecture 10, Part 2. So we left off proving a bunch of languages were decidable, but the motivating idea of the second part of the lecture is going to be that some problems can't be solved by computers. Whoa. I suppose if you remember way back to lecture 1, you'll remember that we showed enumerating the real numbers is something that a computer can't do. We may or may not have framed it in those terms at that point, but we'll see that again. So let's consider this language. In the previous chunk of this lecture, we saw the languages A, NFA, A, DFA, ACFG, where we got pairs of encoded automata inputs, and asked the question, does this automaton accept this input? So we'll consider the same thing for Turing machines. So this is a Turing machine running on an encoded Turing machine. Or sorry, I suppose a Turing machine that decided this language would be a Turing machine that took an encoded Turing machine as input. And maybe a little brain bending, but not actually a problem for us. Like we can imagine a program that takes its own code as input. A Turing machine is a finite object. We can write it down as a string if we want to. We can run a Turing machine on a description of itself. That's totally fine. It's a little weird, but it's completely legal. So we can define this language A sub TM of all encoded TMs and strings such that M accepts W. Doesn't seem implicitly problematic. And indeed, it is easy to recognize. We just simulate M on W and accept if M accepts. So in other words, we just write down a Turing machine that simulates M on W. And if M ever stops and accepts, then our simulation will stop and accept at some point, and we'll accept. The issue is if M does not accept W, if M loops forever on W, then our simulation will also loop forever. It's not easy to see how to turn this into a decider because somehow we would have to detect an infinite loop in M. And as it turns out, that's going to be a hard thing to do. So to deal with this, we're going to have to make a little detour. So let's recall, cast our minds way back to lecture 1. So long ago, we proved that the set of real numbers, that's blackboard bold R with the double stroke there, can't be listed out as a sequence. That is, we said we can't define a sequence, an infinite sequence that contains all the real numbers. We can't write down a program that lists them all out as that lists all the real numbers because there will always be some number missing from that sequence. So we did this by diagonalization. So argument roughly was, suppose for contradiction, some sequence exists and that it eventually contains every real number. And we'll write down our sequence. And imagine we have some sequence. Well, given any such hypothetical sequence, we can prove a contradiction. We can show some number that's not in the sequence. So how we do that is for each number, we cross off a digit from that number, and we make our new number have a different digit. So we'll say, okay, our new number has a different first digit from A1, a different second digit from A2, a different third digit from A3, a different fourth digit from A4. And because we've constructed n to differ from every number in our hypothetical sequence, by definition, n is not in the sequence. It doesn't equal aj for any j because it differs in the jth coordinate. So that was a cool argument by diagonalization. And we'll use a similar idea here to talk about things that Turing machines can't do. So let's introduce a formal definition that we didn't, that we're implicitly doing in this proof, but we didn't specifically introduce. So here's the definition. We'll say a set is countable if it is finite. So far, so good with this intuitive definition of the word countable. If it's finite, you should be able to count all the things in it. Or if there exists a one-to-one mapping to the natural numbers n. So sometimes if you start the natural numbers with a 1, 2, 3, 4, 5, 6, we just call those the counting numbers. And we say that a set is countable if we can map it to those counting numbers. So as an example, are the integers countable? Yep, they are totally countable. At first glance, it might seem like there are more integers than natural numbers because, you know, there's all the natural numbers plus some more stuff. Nah, it's not true. There's the same number. So our mapping says the first integer is 0, the second integer is -1, the third integer is 1, the fourth integer is -2, the fifth integer is 2. And hopefully you can see how if we continued this mapping, we'd eventually assign every integer a natural number. You might also imagine that the set of even numbers, even natural numbers, is smaller than the set of natural numbers. Nah, it's not true either. Because I can define a mapping. I can say, okay, the first even number is 2. The second even number is 4. The third even number is 6. The fourth even number is 8, and so on and so forth. Every even number corresponds to some natural number. So we've shown those two things are countable. And we can say, formally, we proved that R is uncountable. So that's really what we did when we said that there was no way of writing down an infinite sequence of the reals. What Cantor's proof formally shows in terms of this definition is that R is not countable. There's no mapping like this that works, because by diagonalization, we can show that any such mapping would contain a contradiction. If you want to think a little bit harder about countability, you could try this exercise. You can even pause if you want and say, just slightly harder than the ones above, is the set of rational numbers Q countable? So we'll define Q here as m over n, where m and n are integers. So as a hint, I'll tell you that you can think of every rational number as a pair of integers. So really, this problem is reducible to the problem of showing that z squared, all integral points in the plane, the integer lattice over the plane, whatever you want to call it, is countable. So you just got to define some function that'll make sure to hit all of those numbers eventually as you count up. So countability, it just means we can count them. You can say that there's an ordering such that this is the first one, this is the second one, this is the third one, and eventually I will count all of them. And so far we've showed that a bunch of number systems are countable. What if I told you that the set of all Turing machines is countable? So this is well defined. Turing machines are mathematical objects. They're 7 tuples. And this is essentially asserting that there's a one-to-one mapping between the natural numbers and all the possible 7 tuples that represent Turing machines. The proof here is, well, okay, Turing machines are finite objects by definition. So we'll just consider some encoding that we'll denote by the 2 angle brackets with a dot in the middle. So this is just some way of writing down Turing machines as strings, which we've already, kind of seen that we can do. Turing machines are finite objects, so we'll consider some encoding that maps Turing machines to strings over some alphabet. So I claim sigma star is countable. So that is, the set of strings over any given alphabet is countable. And to see this, write down mapping that counts all strings of length O, then length 1, then length 2, ... So for every Turing machine M, let f of m equal k if M is kth Turing machine written down in our enumeration of sigma star. And that's a complete proof, but it's probably a little obscure. So I want to show you an example to make it clear what we're doing here. So as an example, suppose we're just considering the binary alphabet 0, 1. So an enumeration of all the strings over 0, 1 might look like empty string 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, dot, dot, dot. You know, S1, S5, S a million, you know, tons and tons of strings. Just continuing this pattern, writing out every binary string. Definitely something we could do. And now, if we encode some Turing machine in binary, it appears in this sequence. So, you know, maybe S5 over here is a binary string that corresponds to an encoding of M. So all TMs will appear somewhere in the sequence, which creates an ordering. So in other words, all my Turing machines, when they're encoded, will be some binary string. All binary strings appear in this sequence, which means this sequence puts all my Turing machines in order. I could read off all the strings in this sequence, throw away all the garbage strings that don't encode any Turing machine, and I would be left with a mapping from Turing machines to numbers. First Turing machine, second Turing machine, third Turing machine, millionth Turing machine, would eventually get to all of them. So the set of all Turing machines is countable. So that's interesting because it's like kind of a finite encircling property of all the Turing machines. They're pretty wonderful, but they're still countable. You know what's more complicated than the set of all Turing machines? The set of infinite binary strings. To be clear, this is not the same as sigma star. Sigma star is all the finite strings. It's an infinite set. Sigma star contains all the finite binary strings. This is the set of infinite binary strings. And the argument is exactly the same as our proof for the real numbers. If we had, for contradiction, some enumeration of all of the infinite binary strings, well, we could create a new binary string B by flipping the nth bit of the nth string We could say, hey, this new binary string B that we just defined by flipping all the bits of our hypothesized enumeration. Well, sorry, B is not in the enumeration. That's a contradiction. You cannot count the set of infinite length binary strings. This proof does not work for finite binary strings because finite binary strings have a finite length. So you can't always flip the jth bit of a finite binary string if it doesn't have j bits. But it works for the set of infinite binary strings. And okay, so we have that the set of all Turing machines is countable. Set of infinite binary strings is uncountable. Why did we prove these two facts? Because it leads us to this bizarre result, this non-constructive outcome. By non-constructive, I don't just mean that it puts an end to the discussion. I mean, it doesn't give us an example of some property. Theorem. Some languages are not Turing recognizable. Proof. We can encode any language as an infinite binary string. Indicating which elements of sigma star are members. So what's going on here? Well, I'm saying sigma star, if sigma is the binary alphabet, it's empty string, and it's also 0 and 1 and 0, 0 and 0, 1 and 1, 0 and 1, 1. And then if I have some language L, that's a subset of sigma star by definition. Any language over the binary strings is some subset of 0 sigma star. Well, I can encode L by writing down a binary string that indicates which members of sigma star are in L. So we'll say, the empty string is not in L. 0 is in L, 1 is in L, 0, 0 is in L, 0, 1 not in L, 1, 0 not in L, 1, 1 not in L. So what this infinite binary string tells us is, okay, the string 0 is in L, string 1 is in L, the string 0, 0 is in L. And clearly, for any language L, there's some infinite binary string that tells us which strings are in L. Similarly, any infinite binary string gives us a different language over sigma star. If you give me an infinite binary string, I can convert it back into some language of strings. Cool? So any specific language can be encoded as an infinite binary string. So we have a one-to-one correspondence between languages and infinite binary strings. However, we observed that the set of infinite binary strings is uncountable. So by our second observation, the set of languages is uncountable. However, by our first observation, the set of Turing machines is countable. So there can be no one-to-one mapping between TMs and languages. In particular, this rules out the possibility that every language is recognized by some TM. So what the heck did we just do? We said, hey, look, the set of all languages is uncountable. We can't map it to the natural numbers. So suppose for contradiction that every language was recognized by some Turing machine. Well, the Turing machines are countable. So we can count them up. We can say this is the first Turing machine, this is the second Turing machine. And we could use, if we knew that every language was recognized by some Turing machine, we could use the Turing machine ordering to create an ordering over languages. But we've already shown that's impossible. So it's a contradiction. So we end up with this crazy result. There's more languages than Turing machines. So there must be some out there which can't be recognized by any Turing machine. And one reason this proof is crazy is it doesn't tell us anything about those languages. They're like dark matter at this point. We know they're out there. We know there's tons of them. We know they can't be recognized by any Turing machine. We have no idea what they look like. That's bizarre, right? I mean, we'll see a couple. We'll start to get a sense for what a few of them look like. But at the moment, weird. Another way to prove this, if you're really into diagonalization, like you should be, you can imagine writing down all the Turing machines and creating a language of strings such that the nth Turing machine doesn't correctly behave on the nth string. So in other words, you could use the idea that Turing machines are countable to say, well, okay, I'll write down all the Turing machines. And then for Turing machine number 100,566, well, we're going to make sure, we're going to create a language, say whatever this Turing machine does on string number 100,566, we're going to make our language not match that. If it rejects that string, we're going to make our language include that string. So we've essentially diagonalized, creating a language that no Turing machine recognizes. But that's just a hint at another way of proving that. So let's uncover some of these languages, shall we? Let's see what they look like. So our last section of the day, undecidable and unrecognizable languages. So I'm sure you guys are familiar with paradoxes. That is, statements that seem to contain impossibilities. So one famous paradox is the liar's paradox. So if I say this statement is false, what's the truth value of that statement? Is it true? Well, no, if it was true, then it would be false. Is it false? Well, no. If it was false, then it would be true. So if you consider this to be a valid statement, then you also have to accept the fact that you can't always assign a truth value to a valid statement. That's unfortunate. This might seem really trivial, but some people, crazy people, philosophers, computer scientists, think these things are really significant, stay up all night scratching their heads over them. There's another famous paradox called Russell's paradox. And this is a paradox about sets. So it says, consider the set S of all sets that don't contain themselves. Is S a member of itself? So if S is a member of itself, then it does contain itself, so it's not a member of itself. Contradiction. I wrote subset. That's not what I meant. I meant included. If S is not a member of itself, well, then it should be a member of itself because S is the set of all sets that doesn't contain itself. So can show, so what Russell's paradox might tell you is that we can conclude that any foundation for set theory, that is, any set of axioms that tries to make our rules for sets very precise and non-contradictory, well, any foundation for set theory that lets you create a set like S is, we'll say, problematic. In other words, if you create some foundation for set theory, you try to set theory on an axiomatic basis, and your axioms let you create Russell's set, well, then your axioms have problems because they result in this spooky behavior. This is related also to even crazier issues at the heart of mathematics, like Gödel's incompleteness theorem is something you might have heard of. There was this dude named Kurt Gödel, and he said, suppose you have some axioms for arithmetic. If they are sufficiently powerful, then if they're sufficiently powerful, then you can write down some mathematical statement that can't be proven true or false. And that's unfortunate, right? If you ever have axioms that are sufficiently powerful, you get goofiness. It seems like now you're just resigned to a universe full of goofiness or a universe that's way too simple to capture what we see in the world. So people got really unhappy about that. It still makes people unhappy, but it's kind of cool stuff. Just for fun, sometimes Russell's paradox is phrased in terms of a barber who shaves. I said this barber. B shaves everybody who doesn't shave himself, who shaves the barber. Can't be that guy because if he does, then he shaves himself, so he doesn't shave himself. And, you get the same loop. Cool. So, we spent 5 minutes talking about paradoxes. We mentioned that paradoxes come into math and lead to some of the most mind-boggling statements in all of mathematics that are really fun to think about. And we will be using a paradox to prove a theorem today. So in particular, we'll show that ATM, which if you recall was this language M's W, such that M is ATM and M accepts W is undecidable by showing if it were, it would create a paradox. And this is really just a proof by contradiction, right? We're saying if this language was decidable, we'd come up with some impossible scenario. That's just a contradiction. But I like thinking about it in terms of paradox because it does seem inherently paradoxical. So here's this proof. Let's assume that ATM so we're just going to write down the definition again. Let's assume it's decidable. And let's let H be a decider. So if it's decidable, some Turing machine decides it. That means it'll accept on all the right encoded strings and it'll reject everything else. It'll always stop. So, okay, what does H do on some input? Well, H will accept if MW accepts. Here I'm using this parentheses notation to just mean M running on W. And it will reject if M doesn't accept W. That is, rejects or loops, runs forever. Cool. So given H, we can build a new TM. D. So we're just saying, suppose ATM is decidable. Well, then there's some decider for it. And if there's some decider for it, we can use it as a building block. We can simulate it when we're using another TM. All this is legal in the land of high-level descriptions of Turing machines. So the Turing machine D will work as follows. It'll say on input M, where M is a Turing machine, run H on M and M's description, and we will output the opposite of what H outputs. So, okay, this second step, a little weird maybe. But just remember, H works just fine as long as we get an encoding of a Turing machine and any string. So the encoding of M is a string. So essentially what we're saying is H finds out whether M accepts on its own description. So looks crazy, not really super crazy, right? All we're doing is we're saying, suppose we have some Turing machine M. Now, given some encoding, write down this Turing machine as a string and see what it does if you run it on itself. That's something a program can do. H is just a thing that tells us what M does. So H will give us a decisive answer. M accepts itself, or M does not accept itself. And then D, the third layer, just does the opposite of H. So don't worry, we'll walk through precisely how this works with an example. But so far, I just want to convince you everything we've done is kosher. We've built Turing machines based on our assumptions that simulate other Turing machines. So thus, what does D do? So D, run on the encoding of some Turing machine M. Well, it will accept if M does not accept, and D will reject if M accepts M. So this is just following through on the description of D. What happens if we put some machine in? Well, it'll run H on M of itself. H of MW will accept if M on itself accepts. So D will reject in that case. And D will accept in the case where M does not accept on its own encoding. And this leads us to our punchline. What happens when we run D on its own description? Okay, well, so let's just plug this right in to the thing we just wrote down. So D of D, and all I'm doing here is I'm reading off how D works, and I'm writing D where I wrote M. Oops, it's black. So D, run on its own description, will accept if D run on its own description rejects, and it will reject if D run on its own description accepts. Hang on a second. This is bizarre. We've built a machine that accepts if it rejects and rejects if it accepts. Contradiction, paradox, this machine is clearly impossible. And all the impossibility flows from our assumption that H is some decider for ATM. So this is the point where you pause the video and you defragment your brain and you go, get a snack and then come back and work through it yourself. And 5 minutes later, you'll forget how this proof works because this proof is brain melting, but it's also one of the coolest proofs, I think, in all of theoretical computer science. This is saying if we have some decider that tells you when a Turing machine accepts something, well then build a new decider that does the opposite. That's D. And that Turing machine run on itself leads to this bizarre paradox. So thus, H cannot exist. So ATM is undecidable. Cool. So ATM is not decidable. However, it is. We showed this by just saying, we'll simulate it, see if it stops. It is recognizable. So we've already showed that it's recognizable. We just proved via our brain melter proof that it's not decidable. Now, we can also show a specific unrecognizable language. So a moment ago, we argued that because the set of languages is uncountable and the set of Turing machines is countable, some of them must be unrecognizable, but we don't have any examples yet. But now that we've got an undecidable language, it's actually a pretty short hop to finding an unrecognizable language as well. So to do this, I'll introduce a definition. Co-Turing recognizable, or complement Turing recognizable. So this is just a long word for a sentence. It'd be nice if this definition was shorter, but oh well. We just say a language is co-Turing recognizable if its complement is Turing recognizable. So, an example of this, ATM is recognizable. So, its complement is Co-Turing recognizable. This isn't really even a statement about the complement. It's just a statement about the original language. We say that some language is co-Turing recognizable if its complement has this property of being recognizable by some Turing machine. Cool, fine, great. The reason we introduced this definition is so that we can write this theorem succinctly, which is this. A language is decidable if and only if it is recognizable and co-Turing recognizable. I should say Turing recognizable. Okay. So we're coming up with an equivalent criterion for decidability. And this is more jargon than new concepts. It's actually fairly simple to show this. So if A is a decidable language, then it has a decider and ATM can be recognized by the TM that does the opposite of the decider. In other words, this first sentence shows that if a language is decidable, then it's both Turing recognizable and Co-Turing recognizable. Like the decider recognizes the language, which means the complement is Co-Turing recognizable. And its complement is also recognizable because we just take the decider, we simulate it because we know it always stops, and we just flip the outcomes. So we can recognize both the language and its complement. That's pretty easy. Now, if a language is recognizable and Co-Turing recognizable, that is, both the language and its complement can be recognized, decide by running both recognizers in parallel, except if the recognizer for A accepts, reject if the recognizer for not A accepts. So in other words, if a language is recognizable, it has some recognizer. If we run that recognizer, it's guaranteed to stop and accept on a string in the language. If it's Co-Turing recognizable, that means its complement is recognizable. So we can run the recognizer for the complement, and the complement machine is guaranteed to stop and accept if the string is not in the language. So at that point, we know we can safely reject the string. By running both recognizers in parallel, we haven't technically defined parallel computation. So what I really mean by this is go back and forth between two simulations. Run each for a few steps. The reason I'm running in parallel is because for any string in the language, the first one's guaranteed to stop. For any string not in the language, the second one is guaranteed to stop. And that's why I can build a decider, because if I run them in parallel, one of them is guaranteed to stop and tell me either essentially this string is in the language or this string is not in the language. But neither one is guaranteed to stop on all strings. So that gives us this particular theorem. A language is decidable if and only if it's Turing recognizable and Co-Turing recognizable. And that gives us this cool corollary. It immediately gives us an unrecognizable language. Gives us the theorem that the complement of ATM, that is, MW such that M does not accept on W, is not Turing recognizable. Why? Well, ATM is recognizable if the complement was also recognizable, then ATM would be decidable by the previous theorem. Right? This is a proof by contradiction. We're saying we can recognize ATM if we could also recognize the complement of ATM, then ATM would be both recognizable and Co-Turing recognizable. And in that case, by this short theorem we just proved, ATM would be decidable. But ATM is not decidable. So complement of ATM must not be Turing recognizable. Spectacular. Okay, that takes us to the end of lecture for today. We covered a lot of ground today. We jumped theorem, 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 theorem. Big bites, fascinating results, probably a lot to take in. That's okay. This will be our last and our biggest bite preceding the end of the course. I hope you can step back even if some of these things are confusing and recognize some of the beauty that's going on here as well. Next time, don't forget, we will have either donuts or bagels. So come to class if you can make it. I'd love to see you. Again, I will not, I won't shame you if you haven't been able to come to class before, that's fine. We will also talk about time complexity. So far we've only talked about computability, what automata can do. Time complexity asks how fast can they do it? And we'll talk about reductions, which is effectively, if we prove statements like, if I can solve A, then I can solve B. That gives us a lot of new languages B that we can solve. It also says, well, if I can solve A, then I can solve B. And I know I can't solve B. You can kind of flip it on its head and say, well, then I guess I can't solve A either. So we can use these things to develop knowledge of a whole bunch of Turing recognizable, Turing decidable, and also unrecognizable and undecidable languages. So that's all next time in lecture 11, the final lecture of the course. Thanks again very much for watching, and I'll see you in the next one. Bye.